So today we're going to do problems from laws of motion. Personally, one of my favorite chapters. Now, coming to the importance of this chapter in terms of number of problems. For example, last year I think there was one problem in advanced and 2 problems in JEE Main. But in 2017 there were 4 problems in advanced. So the number keeps varying. But it's hard to say that this is hard to figure out the importance of this chapter based on the number of problems, because generally it is just very important, because a lot of the concepts that are covered in this chapter are used in a lot of the later chapters, and it's also very beautiful, right? The chapter itself. Mainly because the whole chapter technically is just one law and all the implications of that law. Almost everything that we can see mechanically can be explained from that one law. Okay, so let's quickly cover all the concepts that are in this chapter. So the first important thing we learn is probably FBDs, right? How to draw a free body diagram if you have a block and if you have multiple forces acting on it, say one here, etc. Let's say gravity, normal force, so on and so forth. To analyze what's happening to that body, we need to separate the forces and figure out what's happening in each direction. For that, we need the free body diagram. And of course, as we do this, we also learn about the different types of forces. There can be friction, there can be tension. For example, let's say if I have a body like this that's moving on some surface which has friction and it's moving because of some force like this, and we learn that friction always opposes relative motion, right? So therefore friction will be in this direction. And of course, in friction itself, there are 2 types of friction. There is static friction and there is kinetic friction, right? Static friction occurs when the object's not moving, where friction is preventing that motion. Kinetic friction is when the object is moving, slipping is happening, and friction is still, preventing, or friction is still, acting on that body. Now, other types of forces include spring forces. If you take a spring, we can see how, if you compress the spring, how much force it will apply. And we know that there's a constant called K, and then it is dependent on the change from its normal size. If the change from its normal size is, if it's compressed by a distance of, let's say, x, then the spring force will be Kx. Another common force that we see often is tension. So we have a block, and let's say it's hanging from some surface via a rope, and the force that this rope applies on this rope is given by the tension that's in that rope, right? Other types of forces include centripetal forces. Centripetal forces, we know, we've already learned about this. Occurs in circular motion when a body is moving in a circle, right? And the force that's constantly pulling it toward the center. For example, let's say there is a stone that's been swung around in a circle like this. The force that's constantly pulling it toward the center is called the centripetal force. And one thing that's important to note here is that centripetal force is not a different type of force. For example, it can come in any form. Like in this case, if it's a string that's pulling the stone, then tension is the centripetal force, right? Tension is the force, and it's centripetal because it's constantly pulling it toward the center. It can be gravitational, it can be electrostatic, it can be any type of force. But if that force is always pulling an object toward the center, then we call it a centripetal force. Okay, these are the broad types of forces that we see. Then once we learn about the different types of forces, we learn about how to resolve these forces. Because let's say we have an object like this that is on some kind of an inclined plane like this, right? Now we know that gravity will always act downward. So let me draw this over here. Let's say this is M. So gravity will be mg in this downward direction. And let's say there's friction. And that friction is preventing this from moving. So let's say it's acting in this direction. Let's say denoted by small f. Now it becomes complicated because these are in different directions. So to simplify things, we resolve these forces. So if I draw the FBD separately, right? I draw the components in two perpendicular directions. It can be vertical and horizontal. It can be any two perpendicular directions. So I don't know, for the sake of simplicity, let's assume that this angle is theta. So if this is theta, there is also a normal force which will act in this direction. So if I resolve it, this will become mg in this direction. So if friction is acting in that at an angle of theta, then this will be f cos theta, right? And over here we have f sin theta, right? Now what will be the direction for normal force? Let's figure out the components over here. So if I draw this line over here, this will be cos theta, and we have n sin theta. Right, all this we know, I'm just revising. So as you can see here, I've resolved all the forces in two mutually perpendicular directions, that is the vertical and the horizontal, so that it becomes easy for us to analyze what's happening in these directions separately, right? And then we can solve the problem. Right, so after this, the secondary concepts that we learn are probably one of the most important is possibly conservation of momentum. Now, technically, conservation of momentum is like an extension of the second law of motion, but still, it can be treated as a separate concept and can be used as a separate technique in certain problems, right? And we also have after that, there's also inertial and non-inertial frames. When the frame itself is accelerating, then we have another technique where we include a pseudo force and so on and so forth. Now, what is the actual second law? Well, we know that it's simply written as F is equal to ma, right? Or F is equal to mass into acceleration. But more specifically, it's F net is equal to mass into acceleration, where F net is the net force acting on this object, and m is the mass of the object, and acceleration is the acceleration of the object. Now, this is true for any system. It doesn't have to be just for an object. If I have a system like this as well, let's say there's two blocks like this connected with one string like this. Now, this is a system. Now, if we know the net force acting on this system, and we know the net mass of the system, then we can calculate the net acceleration of the system. And technically, the third law, which is every action has an equal and opposite reaction, that's actually an extension of this law only. If you, there's a way to explain that. We don't have to go that. Also, conservation of momentum also makes sense because this you can derive conservation of momentum from here, because we can write this F equals ma as dp by dt, where p is the change in momentum. P is momentum. So dp is the change in momentum. So this means that if F net is 0, then dp by dt will be 0, which means that dp has to be 0, or change in momentum has to be 0. And that is the idea or law of conservation of momentum. If the net force acting on a system is 0, then the change in momentum should be 0. Right? So as you can see here, this is also an extension of the second law of motion. So here, again, we have an interesting problem. We have two blocks. One of mass 6 kg, one of mass 6 kg, one of mass 4 kg, and it's connected by an interesting type of rope. We're generally used to massless ropes, but here we have a rope with mass. Right? Now, I know that this might get a little confusing because of that, but I'm going to show to you that it's not. It's actually pretty simple. Okay? So we have this rope which has mass, and this mass is uniformly distributed. What is given to us is B is the midpoint of AC. It's fine. The masses of the blocks are given, and the magnitude of the force is given, which is 60 Newton. What we need to find is the magnitude of tension at A, B, and C. How do we do that? Simple. We have to draw a separate free body diagram. So let's first draw the free body diagram for the big block, the 6 kg block. If you draw the forces, there's one force acting in this direction, which is the force that we're applying, which is 60 Newton, right? And there is another tension force that's coming from the rope. But this is not a constant tension force. This is where we need to be careful, because the mass of the rope is not zero. If it has mass, the tension will keep changing. So let's call this TA for tension at point A. Is there any other force? Of course, there's gravity and there's normal force, but those get cancelled, right? Because there is no movement in the vertical direction, so we don't have to worry about that. So there's only these two forces, okay? Let's draw the... Now, what does this tell us? Nothing. What can we do after this? Nothing. We just have two forces. We don't know anything else, right? So, cool. Let's see if we can get some more information. Another way would be to draw the separate FPDs for each of these objects separately. But one thing we do know is, if you look at the whole thing as a system, that is both the blocks and the rope as a system, there's only one net external force acting on it, which is this 60 Newton force. So therefore, and we know that it's going to be traveling together as a system. So we can calculate the net acceleration of the system. And thankfully, if we calculate that, we'll know that the acceleration of each body separately will be the same, because they cannot move with respect to each other, right? In the frame of the block, all of them will be at rest. You get it? So if we calculate the acceleration of the system, then the acceleration of each object will be the same, right? So let's do that. So the net force, F net, let's call it. F net is 60 Newton. And the mass of the system, right, MS, let's call it mass of the system, is 6 plus 4 plus 2, that is 10 plus 2, 12 kgs. So the acceleration A net of the system, I'm just going to call it A because that will be the acceleration for all three objects. That will be 60 by 12, which is 5. A very simple number, 5 meters per second squared. Right, our units are fine, 60 kgs, correct. So 5 meters per second squared is the acceleration, which means that this block, even the 6 kg block, if you look at it separately, it is going to move with an acceleration of 5 meters per second squared. So which means that because 5 meters per second squared is the acceleration of the system, it's also the acceleration of this body as well, right? As I said initially, because all of them are moving at rest with respect to each other. Which means that if I do the same, F net equals mass into acceleration analysis for this body, it should be the same. So, or in other words, A for that separate body should be equal to its F net by its mass, correct? Which means that 5 should be equal to its F net. What's its F net? 60 minus TA, right? Divided by its mass, which is 6 kgs, right? So this implies that 30 is equal to 60 minus TA, which means that TA is equal to 30 comes this side, so 60 minus 30, which is 30 newtons. So the tension at point A is 30 newtons. Great. Okay. Now let's go to the other case. Now what do? Let's do the 4 kg block, because I think that's simple. So at point C, let's draw the free body diagram for the 4 kg block. Right. This. That is TC, right? That's acting in this direction. That's at point C, okay? And any other forces on 4 kg? No, that's the only force. Cool, that makes things simple, which means that 5 or A, same equation here, F net by M, which means that 5 should be equal to TC by 4. And this very simply gives us TC equals 20 newtons. Right? So as you notice here, TA is 30 newtons and TC is 20 newtons. And the tension is different because the mass of the rope is not massless. Now what do we have to find? We need to find the mass at the tension at point B. How do we do that? Now we know that the tension at point A is 30. Let's write this over here. So we know that this tension over here is 30 and this tension over here is 20. Intuitively, you might think that, okay, because it's the midpoint, it should be about 25, right? I mean, you can think that way, but that's not the right way to do it. We'll have to, let's try to prove it. It's very simple to prove it. So what we'll do is we'll just assume that this object, that is this rope plus this object, this whole system is a separate block by itself. In other words, you can say that block, let's call it AB, let's call it, let's call it P. Right? Basically, half the rope plus the 4 kg block. That together a system, I'm going to call that system P. What are the forces acting on that P? Just this tension at point B, right? The tension from the rope. So if I draw the free body diagram for that, for this system P, there is a tension force in this direction, which is TB, correct? Tension of that rope, pulling it in this direction. And that's the only force acting on it. There's no other force, right? And this system is also moving with an acceleration of 5 meters per second squared, but its mass will be equal to what? 4 kg plus that rope amount. So its mass will be equal to 5 kg, right? Because 4 kg plus half the rope. And half the rope, because the whole rope is 2 kg, then half the rope will be 1 kg. Simple, right? So this acceleration, I'm going to do it over here itself. This acceleration of this system P will be equal to TB by 5 because it's mass, right? And we know A is also 5, which gives us that TB is 5 into 5, 25 Newton. So we were right. It is half. It's halfway. So the force also reduces by half. So it is 25 Newton. So finally, the answer we get is, so TA equals 30 Newton, TB equals 25 Newton, and TC equals 20 Newton. Okay, so we have one more interesting problem over here. So what does the question say? There's a wedge of mass capital M dash. There is a block on top of that of mass small m, and it's connected in such a way using this string like this, and that string is going over a pulley, and there is another another block of mass capital M that's hanging over there. Okay. The question says, what should be the mass of this block? The block of mass small m, this block doesn't slip. Basically, this block should not slip. How is that possible? You might immediately think that there is no friction, right? If there is no friction, all surfaces are frictionless, it's given to us. If there is no friction, then it has to slip, right? How is it possible that this doesn't slip? Well, that's because in this, it's probably because you're just assuming that this thing is stationary or this system is stationary. It's not, because this mass over here is going to pull this whole system downward, and because of this pull, these two masses are going to move in that direction. Okay, and because they move, they're going to move with some acceleration, and therefore there's going to be a pseudo force. You can say that there are two ways of looking at it. Either you can say that there's, because of that, in the non-inertial frame of this wedge, right, in this moving wedge, you can say that there is a pseudo force that will act in this block and that will prevent it to move. That's one way of saying it. The other way is simply that because this wedge is moving in this direction, it'll move in this direction, it'll push this block, right, in this direction. That will have a vertical component which will prevent it from slipping. Right? That vertical component should prevent gravity from pulling it down, so on and so forth. Right? Once I draw the free body diagrams, it will become more clear. So let me just draw the free body diagrams. Okay. Now let's do it one by one. So first, let me draw the free body diagram for this mass. Okay. I'll do it over here. What are the forces acting on it? Of course, there is maybe some other word. Yeah, there is mg, force of gravity, and there is tension from this rope or this string, right? But this is moving. It's moving down. It'll obviously, the net force, it says nowhere that the objects are stationary, right? So it has to move down. So which means, let's say it's moving with some acceleration a, which means that mg minus t is equal to, correct? Let's call this equation number 1 so that we can remember it. Okay, cool. This is the first equation we're getting from the first free body diagram. Of course, there are a few minor things that I'm not looking at. I'm assuming that acceleration is in the downward direction, right? This is something that we don't know yet. We can also do the same problem by assuming it's in the upward direction. We'll finally get a value of a which is negative. But let's not go into all that. We can, because it's obvious that mg has to pull it downward. That's the only way the whole thing will move, right? And there is no friction, so it has to, because all surfaces are frictionless, it has to move downward. So let's assume that this a is in the downward direction. Cool. Now let's go to the next thing. Let's go to the next object. Which object should we take? We'll take the wedge. I'll write it over here. The wedge of mass capital M dash. What are the forces? Let me use green over here. So here we have M dash G acting downward. Okay. Well, there is tension from the same tension force that's coming from that. It's acting over here, right? Cool. T over here, and there is also a normal force that's acting perpendicular to the surface. Let's call it N, a normal force from the block on top. Now, this normal force has a vertical component and a horizontal component, right? The vertical component doesn't really matter to us right now, so I'm just going to resolve this so that things become easy. If you draw directly, this angle is 90 degrees, which means this angle has to be 90 minus theta, correct? This angle will also be theta. Okay? So if I resolve this n into two components, this will become n cos theta, and this will become n sin theta, right? And it's important to remove this now because we've already drawn its components. Okay. So this is not complete. Now this tells us there are horizontal forces, but if you look in the vertical direction, there are two vertical forces in the downward direction, which means that it should move in the downward direction. It's obviously not. What we're missing out here is another normal force from the ground that's coming up, right, and pushing it upward, which is n dash. And technically, honestly, that's not really important for us because you'll see that really doesn't matter to us, right? But anyways, let me write down the equations. Now let's just concentrate on the horizontal direction. Now we know that this wedge is moving with an acceleration a, right? It has to move with the same acceleration as that of capital M because they're constrained. They're constrained by the string. If M is moving down with the acceleration of A, then this wedge should also move in the sideward direction with an acceleration, with the same acceleration A. So T minus N sine theta should be equal to M dash into A. This is the important equation. The vertical direction doesn't really matter to us because it brings in another force N dash, which doesn't really help us out in any way, right? So let's not write that for now. Cool. Let's now draw the free body diagram for this block, the small block. And the question says that this block should be at rest, right, with respect to the wedge. It should not slip over this wedge, or it should not slide over this wedge, which means that let's draw it here like this. What are the forces acting on this block? Now, it's important to note that this block is in a non-inertial frame. Right? If you, there are two ways of doing this. I like doing it this way. Let's assume that this block, we're in that frame that's moving along with that wedge. Right? The wedge is moving. This block is in that frame. It's moving along with that wedge. It can accelerate, of course, in that frame as well. So let's assume we're in that frame. So I'm going to draw one hypothetical non-inertial frame like this. Right? So we are not in the ground frame. Now in this frame, what are the forces acting on it? There is, of course, mg. So this one is small m, right? So small mg. That's acting downward. Fine. What are the other forces? There is no tension on this. Cool. But there is a normal force, right? The same normal force. This normal force that was acting on the wedge, same normal force will be acting on this in the opposite direction. That's fine. Are these all the forces? Right? There's normal force in mg. That's it, right? There's not, because we are assuming that we are in this non-inertial frame, which means that there will be a pseudo force acting opposite to the acceleration, and we know that this frame is accelerating in this direction that is towards the string with an acceleration A, which means that the pseudo force will be m into A, correct? That will be the magnitude of the pseudo force. Okay, again, this is why people get confused. We are applying the pseudo force because we are in the non-inertial frame. We can do the same problem in the ground frame as well. The only difference will be the net acceleration of this will be ma in the opposite direction, right? So that if you're getting confused, okay, don't worry about that. Do it in this frame only. Go to the non-inertial frame and apply your pseudo force. Now, this can lead to some a dash or some other acceleration in this frame itself, but the question says that this block should be at rest in this frame. Basically, it should not slip on this wedge, which means that all these forces should cancel out. The net force in this frame should be 0, right? I repeat again, the net force in this frame should be 0. So how do we do that? Simple, we can just resolve these forces. So what will this force be? Let's find the angles first. So if this angle is theta, then this will be theta, so this will be 90 minus theta. So cos theta will be in this direction. So I'm just going to resolve it quickly. So n will have two components, which will be n cos theta in this direction and n sin theta in this direction. And I remove n now because I've resolved those components. Now these are all the components, and because the question says that this object has to be at rest in this frame, we just have to equate these, right? So we get two equations here. mg should be equal to n cos theta, right? And ma should be equal to n sin theta. Let's call this 3 and 4. Right? So basically we now have 4 equations. We have over here we have equation number 1, mg minus t equals ma. Over here we have equation number 2, then we have equation number 3, and we have equation number 4. And what we need to find is the value of capital M, right, in terms of M dash, M, and theta, because those are the values. So what we need to remove is T, right? We need to substitute for value of T, and we need to substitute N. But you realize that it should be easy to do, right? Oh, wait, we need to substitute for A also. Correct? Yeah, so we have 4 equations and 4 variables. The 4 variables are T, N, A, and capital M, right? But we have 4 equations, so we should, if we do simple algebra, we should be able to find this capital M. So just for simplicity, I'm going to write down all the equations. So here I've just written down all the first 4 equations that we wrote down. So this is 1, this is 2, this is 3, and this is 4. These are the 4 equations that we have, and we have to find the value of capital M. So what I'm going to do first is I'm going to divide equation 3 and 4, or you can say I'm dividing equation 4 divided by 3, and if I do that, I'll find A by G equals tan theta, right? This is what I get. Now therefore, from there we know that A equals G tan theta, okay? Now from equation 3, I'm just going to rearrange, and I get capital N equals mg by cos theta, right? M being small m here, so small mg by cos theta, okay? Now I have a value for A, and I have a value for N, right? Now this I'm going to substitute in the first 2 equations after adding them. So if I add 1 and 2, I do this in order to remove T, right? Because T will get cancelled if I add 1 and 2. I'll get this equation over here, right? And in this equation, I'm going to substitute for value of A and for N that we found out previously. If I do that, I get this equation, right? And then finally, if I solve for this for capital M with this equation, I get this as my final value. So capital M equals m dash plus small m divided by cot theta minus 1. This is your answer. And of course, if you have values for m dash, m, and cot theta, and for theta, you just input these values and find this value of capital M. Look at this question. So what does it say? This is actually a very interesting, and I find this question very beautiful. So we have a ring like this, and we have 2 point masses that are traveling along this ring. The tangential velocities are given to be, this one is moving with the speed of v, this one is moving with the speed of 2v, right? The question says that the objects, these particles move with constant speed, but the question wants us to find out how many collisions will happen before both of them come to this point. Let's say this point is A. The question says find out how many collisions will happen before both these particles come back to the same point A. Now at first glance it might feel a little too complicated, but if you think about it, and if you just look at it and analyze it for a while, you'll figure out what's happening. So obviously there are these 2 particles, one is moving at double the speed. So when will they collide? Obviously when they reach the same position, right? And because they're traveling the same circle, it's obvious that they will collide after the same amount of time, right? So, but because one is traveling at a larger speed, the one that's moving at twice the speed will cover a larger distance in the same time. So let's assume intuitively we'll figure out that it'll be somewhere over here, right? Let's say this is B. Now this is the point where both of them come and collide, right? Let's call this, 1 and 2. 1 and 2. 1 and 2 come back and collide at this point. Why there? Because 2 will travel at a faster speed. Now, how will you figure out where this point will be? And we also need to figure out what their speeds will be after collision. Now, thankfully, we have enough information. We know that both of them have the same mass. Let's say they have the same mass m, and the collisions are elastic. There is no energy is lost during this collision. Now, so first let's figure out where this point will be, where this point will be. Now, intuitively you can see it yourself, because the object, that is object number 2, is traveling at twice the speed. It will cover double the distance, right? Because the time is constant. To make it simple, let's calculate this. So let's say that this is the center, this is point A, and this is point B. How will you calculate? Let's say this is theta. Let's call this theta 1 and call this theta 2, right? Then particle number 1 is traveling through a distance of theta 1 r, right? And particle number 2 is traveling to a distance of theta 2 r. Correct? R being the radius of the circle. Now, what do we know? We know the velocities, which means that, and we also know that they will reach in the same time, right? Because it's a collision, which means that T1, which is will be equal to theta 1 r by v being the speed, and T2 will be equal to theta 2 r by v. Oh, sorry, by 2v, because the speed is 2v, right? And T1 should be equal to T2 because they're colliding, which means that theta 1 r by v should be equal to theta 2 r by 2v. And what does this tell us? This gets cancelled. Theta 1 should be, or rather, theta 2 should be equal to 2 theta 1, right? That makes sense. Theta 2 should be double theta 1. That makes sense because the speed is double of particle 1, right? So how much will this angle be? Now it's become simple to understand, because theta 2 equals 2 theta 1, and also theta 2 plus theta 1 equals 2 pi radians or 360 degrees. If you calculate, you should be able to figure out that this will be equal to, I think, 120 degrees. So this should be 120 degrees, right? And this should be 240 degrees. This angle, right? So this particle 1 will cover an angle of 120 degrees, and particle 2 will cover an angle of 240 degrees. Now, how do we calculate the speeds of these particles or beads after collision? Now, immediately you might think that we can use conservation of momentum, right? Generally, we use that for these kind of problems. But we know that to use conservation of momentum, the net force acting on these particles or acting on the system should be 0. But that's not true here. There is gravity, there is the forces that is applied by the ring itself, so on and so forth. So how can you just randomly apply conservation of momentum? The truth is you can. I'll tell you why. So if you look at these two beads over here, now let's look at the forces. Now the vertical forces are gravity, right? And of course there'll be a normal force from the ring that's acting in the upward direction. And since we know that the bodies or this ring is horizontal, that means that these beads are not moving in the vertical direction, which means that the net force in the vertical direction will be 0. So it's fine. So basically the normal force cancels out the gravitational force. That's okay. But what about in the horizontal direction itself? What about the forces that the ring applies on these beads? Well, because these beads are moving in constant, in circular motion with a constant speed, this proves that the forces are centripetal, right? It's moving through a centripetal force, which means that those normal forces that the ring is applying on these beads will always be toward the center, which means that during collision, there will be no tangential force, that is in this direction, right? In a direction tangential to that ring, there will be no net force on these two bodies or on this system. So we can conserve momentum along that direction, even though there are so many forces. Okay, so let's go ahead and do that. But before we do that, we need to also come up with a positive and a negative direction. So let's say that this direction this is the positive direction, right? So anything opposite to that will be negative. So which means that body number 1 is moving with plus v and body number 2 is moving with minus 2v. Okay, so if we conserve momentum, let me do it here. M, of course, is the mass of the particle or the bead. M into v minus m into 2v. Again, why minus? Because the second body is moving in the opposite direction, in the negative direction. So this is the initial momentum, right? And the final momentum will be, let's call this the velocity with which it comes after collision. Let's call this one v1 and this one v2, right? And therefore it will be mv1 plus mv2. Notice that I'm not using any signs over here, because even though we know the directions will change, we should not bring in the signs, because we don't know the values of v1 and v2. We just keep them as variables and we have to find out the value of v1 and v2, right? Now we have one equation, but of course m gets cancelled out, but we have two variables. We have v1 and v2. So what do? We obviously need one more equation. So this is where we use a slightly higher concept from work and energy. We can use conservation of energy, right? The energy in the system, the initial energy in the system should be equal to the final energy as well. So what is the initial energy? Initial energy will be half m v squared plus half m 2v squared right? This is the initial energy. The final energy will be half m v1 squared plus half m v2 squared, right? So now we have two equations. We have one equation with v1 and v2, and we have another equation again with v1 and v2. Now, I'm not going to solve this. We can solve it. It's not very hard. But if you do solve it, you'll finally find that VA or V1 will be equal to minus 2V V1 equals minus 2V, and V2 will be equal to V. This will be the final value you'll get. What you'll end up seeing is that the speeds will basically get interchanged. Now, this is a concept that we see very often. Like when you take two bodies of equal mass, right? And if they collide with in such a way that the energy is conserved, or basically they collide elastically, if the mass is equal, the speeds basically get interchanged. So if this moves in with the velocity v and this moves in with the velocity 2v, after collision this comes out with the velocity 2v and this comes out with the velocity v. This is generally what happens. We can calculate it using conservation of energy and conservation of momentum. So finally, this is what we get. So the bodies were here somewhere, they collided, but now their speeds have interchanged. So now this is moving with the speed of 2v, and now this is moving with the speed of v. Right? Now, when you see this, you should realize that this is very similar to the initial case. Because the circle is symmetric, the same thing is again going to happen, right? So this ball number 1 or bead number 1 is going to travel double the distance. This is 1 and this is 2. So bead number 1 is going to travel double the distance. So they'll come somewhere over here at a point somewhere over here. Let's call this C. They'll come like this and they'll meet at this point C. Right? Correct? Over here. Now what will happen? Now again they're going to collide. Okay? And what's going to happen? The same thing that happened again. The speeds are going to interchange. This after collision, this will come back. So this came in with a speed of v. So now this will come out with the speed of 2v. Right? Similarly, this came in with a speed of 2v. So this will come out with the speed of v. Now what happens? Now let's say this is 2. This is 1. Now 2 has a speed of 2v and 1 has a speed of v. So it again should be simple. we know what's going to happen. 2 is going to travel twice the distance, but it'll come to a point somewhere over here. But if you remember clearly, this is our initial point. The balls will come back over here. And because of the symmetry, because the angles are, it's going to be, each time it's going to cost 120, 120, 120, it's going to come back to the initial point. And that point will be point number A. So basically, you'll note that it collided once over here. Out of all, right? That is the first collision. And after that, it was the second collision over here. And after that, both of them came to the same point again. So the number of collisions that happen before they come to the same point is 2.
For more videos and live lectures on the JEE, click on the subscribe button now.